looks like the mic is working. It looks like I'm unmuted here 9 minutes ahead of time. Oh dear. We shall see. We've got several people hanging out in the audience. Thank you for showing up live. I'm expecting it's going to go 20 minutes again today. Hopefully the room won't get too hot. In the meantime, we shall see. All right, but I think we believe we have video, we have audio. I see parameterized has arrived. I will wave back, and all right. There's the crazy jam display on the T2 in the upper left there. Yeah, it's like, is something like that going to happen in the black hole architecture? It's like, well, probably not. And if it does, do you think the rest of the machine will continue to function? Probably not. So, you know, yeah, there's a lot of sense in which black hole, all the tensor architectures, focusing on scale out in the sense that they talk about it, but not focusing on robust burst. I mean, there's a couple of senses in which, because it's MIMD, because it's essentially Ethernet-based communication, you could write code that would be robust to something like that happening, but out of the shelf, you know, this is one of the reasons why it is important to build the T2 times. Because that kind of stuff just happens. You don't have to pretend that the time will hand behind your back. You have to deal with the fact that there may be flaky connections between hardware, there may be hardware going up and down, and so on and so forth. And if we were going to try to, if I was going to say, suppose I was going to make the black hole code that I wrote be as robust as possible, it would be an incredible drag because they have bent over backwards, you know, to put hundreds, over 100 of these tiles in every little chip, and they've already weeded out, as a matter part of the manufacturing process, if any of the things go wrong. You know, in fact, some of the chips that you get may have rows or columns disabled because they had, you know, some kind of some kind of manufacturing flaw, and that was built in, so they can sell them as having a smaller number of 10-6 tiles, but still be usable, and they can work around the missing stuff. Hi, W.J. Rasmussen. I don't know. I don't go to LinkedIn, so unfortunately, even if you manage to connect, you'll never see me there, as far as I can tell. I suspect. I mean, I did try it. I set up an account way back when. I suspect the CS UNM-EDU email might have been what I used. That's what I would try. But like I said, you know, if I can convince anyone to join the Fediverse, that's the best place to find me. The T2 tile. Discord is also good, although that's, you know, pretty corporate. I mean, the platform is corporate as opposed to the Fediverse. So we'll see. I thought these crowns were like who spoke first, but Samter was number 2 and then became number 1, and these things are changing around. It's crazy. Anyway, sure. Craig Reynolds, old buddy from all the way back in the 80s in the Haley community with the Boyds. He got a lifetime achievement, whatever it was, at the same conference that I got the education and outreach award. And I really like Craig because he just focuses on doing good stuff. That's the way I try to be as much as possible. I certainly spent a lot of years of my life trying to, do what was expected. Anyway, okay, so I need to probably focus on today's update for the moment. Work with Craig Reynolds, symbolics, very cool. I was a customer, I was a user. My professor was a customer of symbolics. Okay, thanks guys. Hopefully that's not nice. But they wouldn't use a siren, then would they? All right, I'm going to stop looking at chat. I will circle back around afterwards, I promise, and try to pick up anything that I've missed in the interim. But now, I need to remind myself my final little steps here. Hey folks, it's T2sday. This is going to be another long one, I'm afraid today, like 20 minutes. We're on YouTube. Let's start with an unboxing video. All right. Can't have an unboxing without a box.
Alright. How you doing, sir? Okay.
Ancient craftsman drill. is unbelievable. Up here, we're getting to first power on sequence. In fact, that's where we're at. We've got a incredibly ancient VGA monitor. I don't know, I guess I'll just do it. The fan started up, so alright, so here we go. Okay, now we have blue light. They did say that we might have up to like 10 minutes or something on first post. Oh my god, look at this. So we've got bubbles. And we've got air circulating in the reservoir. Is that what this is called? I don't even know. Oh, and now we've got the monitor lighting up, and stuff is happening. Or there was stuff happening. Oh, look at this. I'm not gonna run any of this stuff, but it looks fine. All right, well, hey, step by step, that's it for now. And today we are live, and the quiet box is running quietly over there, and that's what I've been doing for the last week and a half. What I want to talk about today is mostly what I've learned so far and the reactions, and also just the general idea of what T2sday is trying to do. So got a ton to talk about, so like I said, it'll probably go a bit long. The goals for today were baby P4 events. Now, did I really do that or not? Well, it kind of depends on what baby means. In the T2sday lingo, these tiny little RISC-V processors, the black hole chips, are just lousy with them. There's hundreds of them on the chip, and they call the little collections of them baby RISC-Vs. So if baby P4 events means running on the baby RISC-Vs that are on the 10-6 tiles on the black hole chips, I did not achieve that. If we're talking about running RISC-V code to do minimal events in a standalone little bit of code running in a cross compiler, so it's running in the RISC-V architecture, well, I did do that. But have the black hole quiet box. Yeah, it's here. Begin playing with it. I've been doing it a lot. I have been having huge fun. I've been having so much fun. I've been feeling a little guilty. In fact, this is the old kind of master of the universe feeling that you get with deterministic computing, that I get with deterministic computing, where, debugging is a struggle, but it's a game of solitaire that you always win in the end, and so forth. I did not do Ulam. We're going to have to figure that out. Okay, so unboxing and setup, we did it. What I want to do today is talk about this, the architecture, my reactions to the quiet box and black hole and T2sday efforts in general, in this concept of connecting the gap between what you have and what you want, and the various ways that you can think about doing that. And then I want to save enough time to actually try to do a live demo, since one of the main purposes of getting into all of this new architecture stuff is so that we can try to run stuff quick. And if it's going to take time lapse across weeks like it did with the T2 tiles, then we don't want to do that. We want to push that away and figure out how to do as much as we can while still having it move along enough that just looking at it would be interesting. Is this scientifically important? I'm not sure. But is it practically important? It is in its way. Okay. Mind the gap. So I've been saying since the very first, the pilot episode of these T2sday updates, I've been saying a whole new stack. That what we need is a whole new stack. So much so I got a button for it finally. From hardware to software to systems to artificial creatures, who knows? TensTorrent is a company after my own heart because, in essence, that's what they're trying to do, too. They're trying to go all the way from silicon, brand new silicon, with a lot of architectural changes. I mean, the individual pieces of architecture are all familiar. It's not doing anything super exotic computationally, but putting it together into an architecture that's got a lot of complexity, a lot of details, and trying to get to something useful from there. And the question is, in all of these cases, how do you bridge the gap? The gap, in my mind, there's tons of ways to look at it. They're all related. They're all about implementation. Things that could exist, things that could persist. I mean, you can build all kinds of stuff, and I have built all kinds of stuff that fell apart quite shortly. And the bridge between things that could exist and the things that could persist is life. That's the living computation presumption, that what makes something life is that it does work to persist. And similarly, things that we make versus things that make money. That's what business is supposed to connect, or a successful business. Once again, you can easily make things that do not make money. I can exemplify that as well. But it's essentially the same concept. Things that we could have, things that we could want. So the TensTorrent approach, as far as I basically understand it, now this may have involved a pivot somewhere along the way, but whatever, to build these new machine designs in silicon and roll them out and win at machine learning. So in particular, take some market share away from the gorilla in the room, which is NVIDIA, doing this. And so TensTorrent has stuff like this up on their website. And this is all of the AI models, Llama, Stable Diffusion, all of these things that people at the company or people out in the outside world have brought up on various generations of TensTorrent hardware, and they're trying to make it as clicky as possible. You want to try Llama 3.1, 70 billion parameters. Well, you can do that. Here you go. And so on. And so that's an approach. That's the fundamental approach that they're trying to do to bridge the gap between this new architecture and, well, in this case, what people know, which is SIMD, the thing that NVIDIA uses to MIMD or MISD or various other things that TensTorrent is using. And the main trick they're using to try to bridge this gap is open source. And they're putting all this stuff out there, which it's tough. It's risky. I mean, when I first started doing open source, I was kind of ashamed of the quality of my code, and I am still kind of ashamed of the quality of my code, but so is everybody's code sucks. I mean, there's occasional absolutely beautiful pieces for several different notions of beauty, but most of it out there is not, and it's more important to get it out there and let people share it or not as they will. So in particular, the software base that TensTorrent is producing has this thing called Metallium or TT Metal, TensTorrent Metal, and then there's all of the stuff absolutely down at it's close to the hardware as you can get. You read the hardware specs and you write C in assembler code. Now, the funny thing from my point of view is that on the TensTorrent marketing point of view, they talk about TT Metal as being a low-level interface, because a high-level interface from their point of view is clicky and get a large language model, clicky, get ChatGPT one day or whatever it happens to be. And the TensTorrent Metallium level is low level relative to that, but it's really high level compared to going all the way down to the silicon. And on the TensTorrent Discord, there are two extremely competent developers that will answer questions from open source developers and schmoes such as me. Marty 1885 is way up again, from my point of view, way up. At the TT Metal point of view, Core 6 is all the way down at the read the hardware description level, and I was LiveComp, that's me, was in the gap, and to some degree I'm still in the gap, and which way should I go? And so I explored them over the last week and a half. At first I was looking, let's go down low level because we're cool, we're really talented hackers, we want to know what we can exploit, let's go low level. Well, so I downloaded some of Core 6's demos and started working through them, and it was like, holy crap. The upper level, the TT Metal stuff, has a user mode driver that is supposed to talk to the kernel mode driver and make things much easier. In the Core 6 code, we'll just write our own thin user mode drivers. That's all we need. Similarly, Core 6 has no problem not only putting assembly language in comments, but actual binary code inside the C code. And, where's this come from? Not my problem. And, blah, 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 set up the PCI bus with the reconfiguring the bar 0 for the TLB. We could do this. There's code to do this, but we prefer to do it ourselves. And it was like, I couldn't even read half the acronyms in this comment when I first started. I know about TLBs from CPU architecture, but not in the context of PCIe. I am a newbie in PCIe. And all of this terrified me. So I said, okay, let's go for TT. Let's go for some hand holding. And so I started doing demos there, and it was good. There was, I could get stuff going a lot quicker. But it's all these things about the assumptions that the code base makes are not quite the assumptions that one wants. And there's a lot of people who are in this boat, and they are doing things like saying, how does this particular thing work? And Marty 1885, this is a not uncommon kind of response. That is a fairly low level AI. What do you want to achieve with it that's not viable with a higher level ones? And trying to push people up higher, get them away from Core 6. And of course, my problem is what I want to do is not machine learning. I don't care about machine learning. I did machine learning in the 80s. I care about artificial life. So that's not the answer that I'm looking for. And then it gets tougher. What is the solution for the following error? Somebody asks. And the answer is the kernel is larger than what we allow. Now, kernel is what I would call program. If it's your kernel, if it's your program, make it smaller. That's the advice. Make it smaller. What limit are we talking about here? We're talking about a limit of under 8 kbytes. If your program is more than 8 kbytes, it's too big. And it's like, Now, again, for what they're trying to do, the point is putting lots of code on the baby RISC-Vs is not what it's about. The baby RISC-Vs are just supposed to be simple controllers to drive these piles of matrix multipliers and all kinds of floating point stuff and so on. But I'm not doing that, and I own a black hole quiet box. So I pushed back towards Core 6. So I bit the bullet, and I've been doing all this bottom-up stuff, trying to figure out as much as I can, trying to simplify it as much as I can, tear the code apart, move it into various classes and stuff like that so that maybe I can make it more general. And that's where we're at. And so I want to take a couple of minutes, and then we're already running long, but if we say 20 minutes, we're okay, to show you a little bit about running some code on the quiet box, on the black hole architecture right now. So here we are. First, I want to show you some of their code, TTSMI. This is their telemetry. Well, this is their system management interface, TENS torrent system management interface, but the telemetry is the most fun. So we've got device number 0123. Those are the 4 black hole cards in the quiet box. So each of those rows has got hundreds of baby RISC-Vs organized in all crazy ways, and all of those cables that you saw me putting in that we're hopping between are connecting those different 4 devices to each other so they could speak to each other. I haven't tried any of that yet. It's they're running at 4 volts. They're running at 3/4 of a volt, but 50 amps. So if we scroll over, so each one of them is using like 35 to 40 watts to do nothing, just to keep the lights on. The temperature is at 110, 114 degrees Fahrenheit, and it's got this nice little heartbeat going back and forth, like Knight Rider and stuff like that. So that's cool. And and the AI clock is running at 800 megahertz. That's its slow rate. It cranks up to 1.3 gigahertz when it's actually got business to attend to. And so TTSMI is really nice, but as an example of the challenges of the whole thing, when you try to run your own code, now you want to look at the core temperature and the AI clock and see that the core temperature is going up and the AI clock is 1.3 gigahertz. It doesn't work, because at the moment you cannot run, at least as far I've had no success, you can't run a TTSMI at the same time that you're running other code that has the TENS torrent devices open, as far as I can tell. So and that's an example of what happens when you're trying to build a whole new stack, but as a result, you have so long to go from silicon to machine learning that, that all of the layers that you put on, they're not all that well, pounded out, so that the convenience features aren't really there. Okay, but nonetheless, it's useful. All right, so here's my code. I'm going to recompile it. Let's, whoops, that's not what I wanted. That's not what I wanted either. That's what I wanted. All right, so we'll delete everything and we'll go again. So now this is taking some time to compile there. The rest of it's going to go very rapidly once it finishes this compile. All right, it built the online code, it sent it out, it ran, it closed, we're done. So that's an example of where we're at, and this is the kind of spikes, simple little programs that I've been writing for the last week and a half to try to learn how to use all this stuff. And the most important single bit of it is that we've got this, that we're actually have debug printing coming from at this point just the one particular 10.6 tile on each of the boards, but there it is. So we can launch code, and the code that we launch, where is it? Here it is. This is the important point. I'm launching code that's a half a meg in size, not 7 kilobytes. And most of that half a meg is a complete waste that I just wrote to fill up space just to make sure this would work, but it does. Okay, so that's the state of the spikes. Our goals for next time is to have actual baby P4s, meaning running on the baby RISC-Vs on the TENS Torx tiles. Lots and lots of spikes, trying out lots of stuff. I have, does this work? Yeah, I guess it does. I have a new to-do list for myself where I have spread stuff all around. So we want to, I would like to get this BMC access, P4 events, there it is down there, and so forth. We'll see how it goes from there, and that is it. Thanks so much for checking in, whenever you did. I hope to see you next time. Alrighty, looks like 12:20. It looks like we didn't do too badly. I am going to turn the air conditioning back on because it's hot in here. It's double hot. I don't know if anybody saw that, but that's one of the things that's on the, hello, there it is. One of the things that's on my to-do list. Oh, here we go. Music is a bit loud. I apologize for that. And we need Grok in there too. Grok is another AI model. I've seen people talking about Grok, but I don't actually know what it is. Yeah, so I want actually elegant use of a spreadsheet. Thank you. I wanted to go back to that actually. That's what I meant to hit. So here, so yeah, cool the room. that's an issue I really want to deal with. Cool the quiet box. I mean, the quiet box is quiet, but you know, it's got a radiator on the top of it. If you look down at it, it looks like you're looking into a car radiator. There's all these little fins. I took some macro pictures of it, but then I ran out of time trying to put them together today to show it to you. And so I wanna get rid of that heat rather than having the quiet box pump all this heat into the room, which then the air conditioner has to suck out. I'd like to duct some of the heat straight outside. You know, which by the way. Brings up the point which one of my friends was pointing out to me, that you know, essentially it's like, you know, like I'm like running a Bitcoin mining rig now. Now my issue is dealing with the heat, and I'm sitting here contributing to the climate crisis, and you know, a tiny little data center, one. And you know, I admit it. I plead guilty to that. I just hope that there's enough research value, enough learning, enough ideas that can persist, enough ideas for machines that could exist that might lead to machines that could persist, or might help you and I persist down the road with our kith and kin, to justify the watts that I'm burning here, as I look for ways to, you know, palm it off on the outside world. Okay, it's gone now, like that. So cool the quiet box, cool the room, and so forth. BMC access I would really like to get going. That in the unboxing video, that one little extra Ethernet. Can you believe how many Ethernet ports this thing has? It has, you know, 5 Ethernet ports on the motherboard, and then 16 Ethernet on the black hole cards. But and those black hole cards are running at 800 gigabits. I think it's really 400 gigabits bidirectional, but still. You know, my home network just barely graduated to 1 gigabit. And I was actually thinking about that, you know, like, why is it? And there was a conversation going on the Discord of the Tens Torrent Discord about high frequency trading. And could you use the, you know, black hole 400 gigabit Ethernet connections to do high frequency trading? And the response was, well, it wouldn't work very well, because the fastest you can get for connecting to exchanges to submit orders is 10 gigabits, like that, and they're expensive, you know, like tens of $1,000s a month. Only if you want 1 gigabit, then you can have it for as little as a few $1,000s a month and stuff like that. And it led me to think, you know, and one of the comments from Corsics, in fact, is why these AI folks get to be so greedy about how much bandwidth they need, how much communications that they need. And I think the answer is, or at least one way to express the answer to that, is that it's because AI is talking to itself. These links that are connecting black holes together, or more in general, these links in data centers, these super high-speed links that are connecting machines that are collaborating on large language models and so forth together, those are essentially inside the brain of the machine, to the degree it has a brain, et cetera, et cetera. And the whole point of the brain, from one point of view, is to have a small area with extremely dense connectivity. And so, you know, when we have this kind of anemic, more or less serial connectivity, the only way that we can make up for it and get something AI or something brainish is by having it be super fast, so that we can have tons and tons of data moving through these connections. 400 gigabits a second. That's absurd. 800 gigabits a second, and so on. All right, and there we are. Oh, Grok is Elon Musk's AI, the one that does all the Nazi stuff. Grok is the Nazi bar of AIs. Yes, I guess I have heard of that too. And So, Samter, you're saying we need Grok in there too? I'm not. So, is Grok open source? I mean, can you download the weights? I mean, that's sort of the absolute first key to being able to start up one of these models on TensTorrent. The weights have to be available. I don't know if Grok is putting them out there. Maybe it is. Can the heat generated be converted into electricity? Well, if there was cold somewhere else so that you had hot next to cold, then yes, you could generate a little bit of electricity. It's not great. Yeah, I mean, you can use a Peltier cooler in reverse and generate electricity from a difference in temperature. It's not super efficient, but it is possible. I mean, I'm also looking forward to winter, when it might actually be possible to heat the tool room, heat the studio that I'm in right now, using QuietBox, and actually burn less fossil fuels, burn less natural gas to heat the house. Okay, right. XI released the weights for 2.5. Well, so then maybe like that. Again, I feel like a real outsider on the, whoops, I saw some little Hardee's going by there, thank you. I feel like a real outsider on the TensTorrent Discord. I mean, I feel like an outsider everywhere. It's kind of my lot in life. But, try to be cheerful about it. Because so much of what's going on the TensTorrent Discord is all about PyTorch and bringing up neural models. And I mean, they're excited. A lot of folks are excited because they could buy a blackhole card for $700 or $800 or something like that, not a whole system like I did, because I'm a wuss, I'm a weenie, I'm a software loser. They're happy to figure out how to plug things into PCIe generation 5 times 16, all that stuff, and start playing around with implementing this stuff. And it really is a lot of fun. And like I said in the update, I feel a little guilty about how much fun it is. And I've been trying to, be efficient again, and all of this stuff that programmers just do because it's cool and it's fun. But again, my excuse is I have adopted the goal of seeing how much cool looking stuff we can do and have it run fast enough for people to interact with it. It might not be like interacting with a puppy going meow, 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 but it might be like interacting with a turtle, or interacting with a fern that opens and closes every day, or something like that. So I mean, there's lots of time scales between time to first token 30 milliseconds, which is what the AI folks and everything, time to first token, TTFS, TTFT, has been going on and on about in the Discord and around the world. There's a lot of time scales between getting a 200 millisecond response and getting a 2-month response like that. So we'll see how much we can go. I did one of my spikes when I have now set up a pseudo random number generator on the baby RISC-Vs. So in fact, I'm taking yes, time to first pun. Samter is the acknowledged champion, TTFP. So like, I'm going to keep talking just for a few more minutes. So each of these 10.6 tiles, so what I would consider the thing that's going to be doing event windows, the thing that's going to be processing events, and we can think of it at that scale, one 10.6 tile processing one event at a time. lots of 10.6 tiles processing lots of different event windows simultaneously, each one at a time. Each of those 10.6 tiles has 5 little baby RISC-Vs inside it, like that, each with a tiny little bit of its own memory in addition to this shared 1.5 meg of memory. So my current plan, which I've started to implement, is I'm going to have one of those 5 tiny little sub-baby RISC-Vs just generating random numbers. The RISC-Vs can talk to each other in a couple of different ways. This is another crazy thing about the architecture, is that when you don't have a single overarching architectural constraint, like single instruction, multiple data, the NVIDIA approach, that gives you a ton of architectural constraints. You say, okay, we want to keep everything as simple as possible so that the multiple datas all can do the same instruction, so they all need to be the same as each other, and so forth. Once you give that up and go to multiple instruction, multiple data, it's like, every multiple instruction could be different. There's no real architectural constraint. So so there's lots of little, you can communicate between these RISC-Vs using the mailbox. You can communicate between these others using the PC bus, and so on and so forth. And so what my goal is for one of the spikes, I might have had it working today, but no, there's way too much learning I still need to do before we'll get to it. Is have one of those tiny little spikes using its own private memory to run the random number generator, to run Mercer and Twister, and to feed the next random number generator through the mailbox system to the thing that's actually doing the heavy lifting of the main event, so that it doesn't have to spend cycles to remix the generator, and more importantly, it doesn't have to either use its own private memory to store the state of the random number generator, or use the system RAM to store the tile RAM to store the random number generator state, because that's both precious, the tile level RAM, and it's also slow. So I'm going to burn a whole processor that's just going to sit there mixing random numbers, provide the next, it'll fill up its little buffer saying here's the next 4 random numbers, and it'll just wait until the other side plucks one off, and then it'll put one in, and so forth. So, and then I still have 4 processors left for every single tile. So it's a lot of fun. There's a lot of hardware. There's a lot of stuff that you can make happen. So I'm enjoying it. It's been a long time. All right. So I guess did I respond to pretty much everything? I think I did. Music is a bit loud. Now that was, I guess, well, I have notorious audio problems. I apologize. I'll try to binary code. I think we talked about everything. At what layer in the current stack would a Demon Horde sword apply? Great question. Thank you, SciSpeed. So over on the here. So we need all this hardware stuff. We need a bunch of this firmware stuff, so that code multicast would be nice. Deploying code to 150 tiles is going to take a while, even Ethernet is fast. All this, the debugging stuff in particular is, essentially priority number 1. That if you're going to, set, I've already written code to set up the environment, to initialize a stack pointer. I already have my code running before the C++ code even begins. I call main. Not the reverse, as is proper in embedded code land. That's the way that works. And so step 1 is get as much debugging stuff going as possible. So we need a bunch of, well, or at least a first round. And so most of this stuff here is going to need to happen. We get to baby P4 events, which we already have running in simulation, and those are really, really very simple. And we get them running on the big R5. And the next big step after that is MFM X10 on the tiles. So that's going to be the event windows, the associated support with that, the UREFs that I talked about a month or so ago. Get all of that working, and once we get to that, we can get to event processing, or at least we can make a few spikes at event processing. And then in the more to do that we've got down there, where is more to do? Here it is, that we've got down here. That's where Demon Horde would go. I mean, after we get baby P4 events, if we wanted to, we could write Demon Horde Sword directly in C++ to do the transitions, to do the dereg, to do the sorting, and so forth. And then we could run it on the MFM X10 on the individual tiles. And if we had the MFM display spikes running back on the host, we might be able to see what it's doing. All of that is, yet to be even specified, let alone implemented. But basically, the important point is that event processing, fork bomb, dreg, and res, Demon Horde Sword, and so forth, is all off the bottom here. And since we're doing bottom up, this is the lowest level stuff up here. We're getting higher and higher level code down here. So Demon Horde Sword is high level code from the point of view of the development we're doing here. Exactly how would we express that in a more compact form than C++? We shall see. Do we have some kind of Ulam-like language or some kind of other language? All of that remains to be worked out, to be designed, to be implemented, to be debugged, to be played with. So that is what's going on with my buttons here. Right. I don't know what's going on with my buttons. I guess that's what's going on with my buttons. Okay, so we're past the bottom of the hour. Again, folks, in the chat room, this is, well, yeah, WJ Rasmussen 666. I'm already thinking about new languages, and there's new versions of old languages. Everything's on the table. I talked several months ago now about NAFI, not a fourth interpreter, a stack-based language, and one of my fantasies, and that's all it is at this point, is to build a stack-based NAFI-like language to express event window transitions and provide access to the UREFs that we've talked about a couple of months ago, the reinvented Ulam refs, to get at the individual fields of atoms and so forth and work it from there. And then, maybe do a little simple infix to postfix translator to generate code for this little stack machine and go from there. Maybe retarget Ulam. We'll see what seems doable as we move on down the road. But if there's going to, again, if you're going to do a whole new stack, you cannot stop at any level, right? So, like Conway's Game of Life, people develop, these unbelievably gigantic, complex patterns that do compilers and do, implement themselves and all that kind of stuff, taking up huge area. And space and time volumes to do these implementations, all of which is only possible because the game of life is synchronous and deterministic and error-free and so on. So you can do that kind of stunt to a limited degree, as long as you can pretend that you've got determinism and synchronous behavior, globally synchronized behavior. But I don't assume that. And the black hole architecture folks are sort of, they're kind of mushy around the edges. Same as the high performance computing folks. When they were talking about exascale supercomputers, for a while they were talking about non-deterministic stuff. But in the end, they kind of chickened out. And in fact, I mean, one of the more interesting things, at least if you're doing machine learning, about the tens torrent stuff is their matrix multipliers take 4 rounds to get the correct answer. But you can stop the matrix multiplication after 1 or 2 rounds like that and get a pretty good answer, like to 4 significant bits or 8 significant bits or something. I don't know the details. More quickly. So that's already a trade-off, giving up on absolute correctness, throwing absolute correctness away, but not for robustness, but for speed, for yet more efficiency. So again, if we're trying to say how could we climb up higher and higher and higher, part of climbing higher and higher is that you'll always need a new language. At every new level, you need to take your next level is going to be bigger and slower than the current level that you've got, and it's going to take these marvels of complexity and treat them as marbles, treat them as raw materials to go into this next larger thing. Society, individual versus society, that's a major transition, that's a level transition. There are new languages for society. And of course, one of the things talking about symbolics back in the day, they were all in on there's only one language. It's Lisp from the bottom to the top, essentially. And I was totally into that in the 80s, and versus Dick Gabriel, who was the defender at the time of the Unix approach, where you have Bash and you have C and you have all these different languages that apply at different levels of complexity, and it seems like a big mess compared to saying, well, the one beautiful language, all you need is Lisp, like that. But if all you need is Lisp, then it isn't really Lisp, right? If all you need is Lisp, then what you did is you wrote def macros to define a new language that compiles into Lisp on the fly, and then you do on top of that and on top of that and on top of that. And so the fact that it's all Lisp at the bottom is not exactly relevant for the expressibility and efficiency that you get at any particular level that you have in the hierarchy. You still have to decide def macro this versus def macro that, and that's going to affect your expressiveness and your computational reach. And that's making a new language. That's doing the same thing. And all right, so you might need a new language. Yes, always going to need the new language. Trying to and the meta object protocol, the Brian Smith stuff, all of that. It's beautiful in its way, but from my point of view, also inherently doomed in its way, in the what it kind of explicitly or implicitly holds out to say that this might be what we could get to, God's language, the only language you need, and so on and so forth. No, we have to earn our way up the stack. There are new capabilities and obligations and new tricks and failures at every level of complexity. Every time we go bigger and slower, there's a whole level of stuff that is qualitatively not predictable by the lower level stuff alone. Because the whole point was we pushed all of the interactions to the edge. When I said the answer is a CPU and RAM, and then all we need is input and output to the rest of the world, I'm pushing all the complexity of interacting with the rest of the world to the edge. and saying the CPU and RAM only has to deal with the program and the CPU and the RAM and the stuff that's in there. And that's fine, and that allows you to do all kinds of great things within that. But you took out this IOU. You pushed all the complexity off into the I/O. And once you go to the next spatial temporal scale, all of that stuff that had been inside is now inside. All the other CPUs and RAMs that are all inside the same machine, now you have to deal with it. So, there's no trick to it. There's a reason why you organize at a given space-time volume, a given speed and space, at a given level, and you take advantage of things that are only true at that level. Like you could ignore stuff that takes longer than 20 minutes because I'm making a little routine that's going to be finished in 20 milliseconds. So I'm going to assume that the 20-minute stuff is fine. Either it's not there at all or it's there for the entire length. Either way, I don't have to deal with it. That's the kind of example of what you can do when you're at a small space-time volume, that once you start scaling up to bigger space-time volumes, it all comes rushing back. And that's why the fantasy of having the one thing that scales across all space-time's volumes, sorry, can't have it. Okay, well, thanks folks so much for staying to chat afterwards and bringing up the topics. I'm gonna call it and get back to cutting the update to try to put it up. It does seem like the updates tend to do a little better if I manage to get them released sort of quickly like that. So we shall see. Again, thanks folks. I love doing these things. I love talking to folks. I mean, I think about maybe we ought to try to have a public meeting again, but I'm not sure if we have any people who are into it enough that they'd want to put their face on the screen and yak about it, or I mean, I would yak about other people's stuff like that. Yeah, David, a lot of work and fun to do, and nice when they come together. Got lots of other stuff to do too, but of course that's always the case. Okay, anyway, thanks folks. I'm gonna put some hearts on for you guys. Whoops, where is it? There it is. Okay, those are hearts from me for you guys. And that's it. So I'm gonna go end the stream is what I'm gonna do here. Be careful, don't end the stream. We're gonna end the stream. That's it.